Calorimetry specifically for combustion. So let's have a look at that. Specifically for combustion. And we're going to use a favorite snack that we all love, peanut butter. So a sample of peanut butter. Let's say is placed into a container. And this container needs to be filled with oxygen. So with oxygen, okay, with a ample amount of oxygen, because if we want to do combustion, oxygen is required, and we want to burn this completely. Okay, so I'll also put here burned completely. So it's complete combustion. And when I talk about that, that means that there's only going to be two products, favorably, the CO2 and the water. That's all we want. So once that is burned completely, it's going to be filled within this chamber, right? So this container, it has oxygen, it's burned completely, but it's also with water. Okay, liquid water, and this is obviously gas. It's going to be filled in this water, so it has a surrounding of water. So a sample of peanut butter is placed in a container surrounded by water. And this chamber, right, that's containing this water is known as a bomb calorimeter. Now, it doesn't have to be a bomb calorimeter, but for this specific example for peanut butter, we use a bomb calorimeter. So again, it is a container that is filled with oxygen and filled with water. And when it's burning, we don't want any energy to escape. That chamber is a bomb calorimeter. Maybe I'll put in here, no heat should be released outside of the calorimeter. So we know that the water is surrounding the substance in question, the peanut butter, but that's about it. We don't want any other form of energy to go outside of this water, outside of the surrounding. Remember in the previous video, okay, about surrounding versus environment? Please have a look at that video as well before you continue with this. So this surrounding is where we just want the energy to go to. We don't want it to go outside of the surrounding, which would be the environment. So please reference that video previous to this one to look more about that. So no heat should be released outside of the calorimeter. And then we have to ensure that the amount of heat that is absorbed is going to be measured. So I'll put here, heat will be measured based on the change of temperature of that water. And that's honestly how we find the amount of energy content that the peanut butter has, by burning it and seeing how much heat goes into the water. So let's have a look at an example. Let's say we have 16 grams of peanut butter, so I'll just put PB. Actually, PB would be lead, so how about I just put T, okay? So peanut butter. Okay, so we have 16 grams of that, and let's say we have a bomb calorimeter. And let's say its specific heat capacity, so C is 8.28 kilojoules per degree Celsius. And its temperature change is 50.5 degrees Celsius. How are we going to solve this? Well, we have to first look at our first question here, which should be quite simple to do. What is the heat absorbed by water? And then a second part to that is, what is the calorie content? Per gram of peanut butter. is for peanut butter. So let's have a look at A first. What is the heat absorbed? Well, heat is just going to be Q, the amount of heat gained or lost, right? So we have to use our Q is equal to mCT formula. However, when we talk about water, because water is within this calorimeter, do we have any mass for the water? Unfortunately, we do not. So we don't even have to put this here. So we can just put Q is equal to CET. We have mass for the PBT, but we don't care about the peanut butter right now. Okay? Whenever we care about the heat absorbed from a particular reaction that's going on, like in the previous videos, all of the heat needs to be absorbed by the water. That's all we care about when it comes to this formula. So because we don't have that, we're just going to put CT. So Q is equal to a specific heat capacity, which is 8.28 kilojoules per degree Celsius, and we have to multiply by the temperature change, which is just 50.5 degrees Celsius. We're just going to continue this over here. So our Q, we'll just punch that in together, and I get 418.140 kilojoules, because obviously this and this cancels out. So that's all we have. So this here is the heat absorbed. Now we can do B. What is the calorie content? Well, we have this much kilojoules that has been absorbed from the water. Well, where did this energy come from? Did it come out of nowhere? Is this magic? No. It came from the peanut butter, the burning of that peanut butter. So that means the burning of the peanut butter released this much energy so that it can go into that water, right? Because this formula was talking about the water. So this came from somewhere. It came from that peanut butter. So if we want to know the calorie content of that peanut butter, it definitely released this much energy. So we know this formula, delta H is equal to N times delta HR. Okay? And this thing over here is the total amount of that heat released, right? This much got released to go into the water that is within that calorimeter. Okay, remember this Q absorbed what this released. They're the same value. So I'm going to be putting, again, this has to be a negative value now, right? So it has to be negative 418.140 kilojoules. That's how much I got released. And then the amount of moles, we don't have it. So we might not even need to be using this formula anymore, because we don't have the amount of moles. It's just peanut butter, right? We can't get any, molar mass value for that. And this, our molar enthalpy here, isn't exactly what the question is asking for, because it's asking for per gram of PBT rather than per mole, right? Rather than the enthalpy per mole of it. So we can actually just kind of scrap this and use a simpler version of, again, this was released by the peanut butter, right? So we'll just put 418.140 kilojoules per gram of PBT. Well, this much got released, right, from that peanut butter. How much peanut butter did we have? We had 16 grams, right? So I'm just going to have to divide by 16 grams of peanut butter. So if I wanted to find it per gram, if I divide them, I'm going to get it per gram. So I'm just going to get 418.140 kilojoules divided by 16 grams. So that's going to give me 26.13 kilojoules. And this is going to be per 1 gram, right? Or per gram of peanut butter. That's it. And if you want to make this even more fine and dandy, kilojoules is equivalent to calories, right? Or kilocal. So when you look at the peanut butter at the back of the grocery store, right? The amount of, calories per serving. Let's say the serving is 16 grams, okay? Then how much calories is it? Well, it's going to be 418 calories. Okay, per 16 grams. And I mean, that's kind of ridiculous, right? This peanut butter is extremely calorie dense. Most peanut butter is not like that. Probably for 16 grams, I assume it's like 100 calories, okay, or 100 kilojoules. But in this case, it is 418 calories. Okay, because I'll just put here kilojoules equals kilocal, which equals just calories. All right, cal is not calories, kilocal is calories. Okay, so this is our little legend over here. So that's the answer. What is the calorie count? Calorie content per gram? It's 26.13 calories. Okay, per gram of peanut butter. But on the back of the grocery store, you'll likely be seeing this, right? Per serving or per, whatever grams is stated on the back. So it'll be 418 calories, okay, per that serving or per every 16 grams of peanut butter. All right, let's have a look at this question. Predict the final temperature of 500 grams of iron ring that is initially at 25 degrees. So we can just put here, it was initially at 25 degrees. So the temperature initial here is just going to be 25 degrees. So just write out our givens as we go along. And we have a 500 gram ring, iron ring, for a mass, okay, of the iron. I'll just put Fe, and is heated by combustion of this much ethanol. Okay, so we have another mass here, which is ethanol, of 4.95 grams, okay, of C2H5OH. Okay, and we also have delta H comb is this many kilojoules per mole. Okay, so this is the molar enthalpy. Okay, so what we're used to seeing for this one is what I usually write out is something like that, okay, for comb, but either one, okay, works. And again, these are not standard conditions, so we actually don't need to put that one over there, okay? So because obviously this is not a not symbol, so that's a not symbol, we don't need that, it's not a standard condition, okay? They already, whatever it is for the combustion of that, they've already given us that here. It's not a preset value. Okay, so let's continue with this. Predict the final temperature. We obviously know a formula that has temperature in it, so Q is equal to mCT. This is our beloved formula, and let's continue on with this. We have a certain amount of mass, okay? We only care about water. Do we have water in this case? No, we don't have water. So it seems like rather than water as our medium that is going to be absorbing the heat, which we're kind of used to seeing so far, right, with our questions that we've been doing together, it seems like this case, we're not actually going to be using water as that medium. It's actually going to be the iron ring. It's obviously not ethanol, right? Because ethanol is the substance that is burning. So it has to be this one. It can't be anything else. So let's use that. So Q is equal to our mass here. It's going to be 500 grams. Okay, now however much this increases in temperature, we'll figure out how much heat got absorbed, okay? It's not going to be water this time. It's going to be this iron ring, which is fine, okay? And our C here, our specific heat capacity, it's not written here. Do we have it anywhere here? Well, it seems like we have one right over there, right? This is the iron, okay, the iron ring. So it's going to be 0.449. Okay, joules per gram degree Celsius. And then we have our change of temperature. Well, we don't know what the change of temperature is. We do know, however, that it was initially at 25 degrees Celsius. So we can put TF minus 25 degrees Celsius. Okay, well, if we have this as an unknown value, that's the only one that we can have. This can't be unknown, so we got to figure out what this one is going to be. How can we figure out what the Q value is going to be? Well, what we do know is within our ethanol here is that it releases this many kilojoules per mole. Well, if that's how many kilojoules per mole there is, can we find out how much total kilojoules is being released? Not per mole of ethanol, but the total amount of kilojoules. Because if we figure out how much total energy is being released by this ethanol, where the heck is it going to go? It's not going to disappear into thin air. It's got to go somewhere. It's going to literally go into this iron ring, because this iron ring is surrounding this ethanol. So whatever gets released from this ethanol is going to go in its surrounding. And like I said, the surrounding is the iron ring. So let's try to figure out what the amount of heat released total is. So we have our beloved formula here as well. Okay? And again, this here, okay, is going to be our total heat We don't know what it is, so I'm just going to keep it as delta H. Do we know the amount of moles? Yes, we do know the amount of moles. We have this many grams of ethanol, which is, I'm just going to put it maybe here on the side, okay? We have 4.95 grams, okay, of ethanol, and we can easily change this into the amount of moles because we have its formula, C2H5OH, so we can just multiply by its molar mass. And again, I need to put grams diagonally together so that they can cancel out because I only want moles, okay? Remember, this is technically all over 1, okay? So we're just dealing with fractions here. So you can just find it on your periodic table. Look for the molar mass of ethanol. Just add them all up, right? The C2H5OH. So I can see it here, 46.08. So I have 46.08 grams per mole. So this grams and this grams cancels out. So I end up just getting this times mole divided by that. So what do I end up getting? I get 0.10742. All right, so that's how many moles I have. So I'm just going to put this into the amount of moles. So I'm just going to be putting 1.0742 moles. All right, and I need to multiply by our molar enthalpy. Do I have that? I absolutely do. Negative 1234.8 kilojoules per mole. We're good here. So then this moles and this moles cancels out, right? They're diagonal because technically this is all over a fraction, right? So diagonally they're the same. So let's cancel those out. So we're just going to be left with our amount in kilojoules. So I'm just going to quickly punch it in my calculator here. This value times this value. So I end up getting negative 132.64 kilojoules. So this is the total amount of heat energy that got released. So I'm going to be putting this into my Q value. So let's put that into there. So I get negative, oh, sorry, this is in kilojoules, right? So let me quickly change this into joules because I have to deal with joules over here anyway. So I've got to cancel out the joules, right? I only want degrees left, right? Isn't TF supposed to be in degrees Celsius? Okay, so I definitely don't want joules anymore. So I got to get rid of that. So let's quickly change this into joules. So negative 132.640 joules. And let's put that in there, okay? So, oh, by the way, again, this is a negative, right? Because this is what got released from that ethanol. But once that gets released, it now gets absorbed from the, sorry, it gets absorbed into the iron ring. So the iron ring should increase. Okay, it's endothermic now, so it's going to change into a positive value. So I have, instead of negative 132, I have positive 132.640 joules, and this is equal to 500 grams multiplied by that value, 0.449 joules per gram degrees Celsius, and then I have TF minus 25 degrees Celsius. Okay, all right, so I'm just going to divide this all, right, by 500 grams times 0.449 joules per gram degrees Celsius. So if I get rid of all of this on the right side, I need to do the same thing on the left side of the equal sign. So same thing, 500 grams times 0.449 joules per gram degrees Celsius. So again, this joule and this joule cancels out, and this gram and this gram cancels out as well. So then we're just left with that degrees Celsius, which is great. Okay, so I'm just going to first divide this by this value here. So what do I end up getting? I end up getting 590.82. Okay, and again, this has to be in degrees Celsius. Okay, and then what do I end up having here? This is now left alone, so I have temperature final minus 25 degrees Celsius. All right, and again, I just need to isolate this, so I just need to plus this side by 25 degrees Celsius, so then they cancel out. What I do on the right side, I need to do on the left side, so I just get 25 degrees Celsius, and then I end up just getting temperature final is equal to 615.82. degrees Celsius. So this here is the final answer. All right, let's look at this question over here. The equation below represents the burning of carbon disulphide in a calorimeter, okay? What mass of CS2 must have been burned? Okay, so we're trying to find the mass of CS2. To increase the temperature of this much water, okay, so we have this much water. 1,000 grams, okay, or 1 kilogram, okay, and this is again of water, and it increased by 15.5 degrees Celsius. So we'll just put that here. Okay, in our calorimeter that we're talking about, it seems like it's filled with water. Okay, so we're definitely going to be using a specific heat capacity of liquid water over there. Okay, 4.19 joules per gram degree Celsius. We're not using a iron ring like the last example where it didn't have water as a medium. This one does. So we're going to use our beloved formula, Q is equal to mCT. Okay, we're trying to figure out the amount of mass that this one must be burned. So we're not trying to find this mass. Remember, this is always regarding the medium that is absorbing it. Okay, in this case, it's not the iron ring, it's the actual water. Okay, we have water within this calorimeter. So this M over here is dealing with the water. It's not dealing with CS2. So we're not going to be finding this M. We actually have this M already, okay, which is this one over here. So we're just going to write it out. Q is equal to 1,000 grams. Okay, multiplied by our specific heat capacity. We have specific heat capacity of water, okay, is 4.19, so 4.19 joules per gram degrees Celsius, and then we have our change in temperature, which is just 15.5 degrees. Okay, so let's just plug this all into the calculator. I end up getting a value of 54,945 joules. Okay, so that's how many joules, okay, that is being absorbed in that water. But now we have to find the mass of CS2. How do we do that? Well, this here is the amount of energy that has gone into the water. Where did it come from? Well, it obviously came from that burning of CS2. So this came from the burning of CS2. So that means our delta H, right? We have this beloved formula as well, right? You're all familiar with, okay? This delta H over here is pretty much this, because when we burn, remember this here is for the CS2, when this got burned and it released energy, it didn't vanish, it went into here, it went into the water. So technically this value here, okay, and it has to be a negative value because it got released, whereas this one was absorbed, so this one has to be negative 64,000 joules, okay, and it's equal to the amount of moles. Well, do I have the amount of moles? We don't, but when we do find the amount of moles, that'll be awesome, because isn't the question also asking for the mass of that CS2, right? This is moles of CS2. If I can find the moles, okay, I can easily find the mass of the CS2. So I definitely need to find this. I'm going to keep this here. I need to isolate it because I want to find it. Multiplied by the molar enthalpy of CS2. Do I have that? I absolutely do. So this is 1690 kilojoules of the whole reaction. However, as you can see, there is only 1 mole of CS2, so that's perfect. So I don't need to change this around. I can just keep it as 1690, okay, kilojoules. So this is 1690 kilojoules, okay? Now, I know this is in kilojoules and this is in joules, so rather than keeping this in kilojoules, maybe I'll just change it to joules, okay? So I'm just going to add 3 more zeros here. So now this is the amount in joules. So now I can easily just find my N value. So I'm going to divide this by 169. 0, 0, 0, 0 joules, and then do the same thing on this side, 169, 0, 0, 0, 0, and then just cancel these out. So I end up getting my N value of, just punch it in my calculator, I get 0.0384. Okay, and this is in moles over here. Perfect. So now I have this in moles. I'm just going to bring it over here. I have this many moles of CS2, so I'll just write it more cleanly here. This is moles of CS2. And I'm trying to find what? Grams of CS2. Okay, so remember, technically everything is over 1, so this is over 1. So diagonally, they need to cancel out. I don't want moles, I want grams. So should I put grams here, or should I put grams here? Or should I put moles here, or should I put moles here? Obviously, moles has to be on the bottom, because that way they can get gotten rid of. Okay, because they're the same value. So I want moles on the bottom and I want grams on the top. Okay, so this is moles of CS2. So for every mole of CS2, okay, how heavy is it? Okay, what is it in grams? So what is the amount of grams? So I'm just going to use my periodic table here, look for the molar mass, okay, of CS2. I end up getting 76.15. CS2 cancels out, this moles of CS2 cancels out, so I end up getting just the product of that. So I end up getting 2.93 grams of CS2. That's your answer. Sample of acetone. In case you don't know what acetone is, it is also known as propentuone. Okay, again, if you haven't learned organic chemistry, don't worry about it. But if you have learned it, so this propane, right, this just stands for prop, right? So there's 3 carbons, okay, bonded together. And then obviously there is on the second, so this one over here, there is an one, okay? So I'm just going to be putting a double bonded oxygen there. So this is completely stable. So I'm just going to saturate these with the hydrogen. So this is where we're done. So we have C3, okay? So we have 3 carbons, and then we have 1, 2, 3, 4, 5, 6. We have 6 hydrogens, and we have this oxygen here just left. Okay, so this here is our acetone or propan-2-one. Okay, we have a certain amount of mass of it, so its mass is 1.920 grams. It undergoes complete combustion in an insulated calorimeter, okay, and it holds this much milliliters of water. Okay, so I can also put mass of water here of H2O. It's 400 milliliters. It's also known as 400 grams, so that's good there. So I'm just going to leave that there. And it is determined that the water and calorimeter together absorb this much heat energy. Okay, so this is interesting. If they both absorb that, we're kind of already done. We don't need to find this Q is equal to MCT. Okay, you probably started it doing that way, right? Q is equal to MCT. However, we don't really need to do that because it already said this, the Q, right? Together, they absorb this much heat energy. So this question already kind of did it for you. It said in total of this Q and this Q, if you did those formulas together and you added it up, it's already given us this Q value here, right? The total amount of heat, okay? So this here is going to be our 58.829 kilojoules. I'm just going to write this here, 58.829 kilojoules. Okay, is equal to the MCT, but I've already figured that out, okay? It's already given to you, so I can just kind of put Q is equal to that, okay? So, all right, so Q is equal to that value. So it is determined that that was the value based on this information. What is the standard molar enthalpy of combustion for acetone? Okay, remember this here is for the water. That acetone, when it got burned, released a certain amount of energy. It released this much amount of energy because water is now holding this. Okay, the water and the calorimeter, excuse me, okay? This here is the water and the calorimeter, okay? So the calorimeter, okay, and water, okay? So it absorbed this much energy. Where did it come from? Obviously, it came from the propan-2-one, the acetone. So this here got released from the acetone. So maybe I'll write that here. It got released, 58.829 kilojoules, okay? Again, I put it in negative because it got released. What is the standard molar enthalpy? Well, we know our beloved formula, N, right, and our molar enthalpy. Well, our moles, do we have that value? Well, we don't have it right now, but we could easily find it. And then what is going to be left over at the very end that is isolated? Our molar enthalpy, our standard molar enthalpy. Okay, that's what we're looking for anyway, so this is perfect. And it, again, it's looking for it in kilojoules per mole. I have already kilojoules, so we're very, very close. Well, how do I find the amount of moles over here? Well, this here is 1.920 grams. So I'm just going to maybe write down here 1.920 grams, okay, of our propan-2-one. And I have to put grams on the bottom so that they can cancel out, so I can end up getting my moles. Okay, so every mole of that, how heavy is it? Well, just look on your periodic table, find the molar mass of C3H6O. I'm just going to be doing it here. So I have 58.09. Okay, grams per mole. So if this multiplies by this and then divides by this, what do I end up getting? I end up getting 0.03305 moles. Okay, and again, this is all for the C3H6O, right? C3H6O. All right, so that's the value. So I'm just going to be putting this moles into there. So I'm just going to copy and paste this again. So 58.829 kilojoules is equal to this many moles, so 0.03305 moles multiplied by my isolated value here, my standard molar enthalpy. So just divide this by 0.03305 moles. If I do it on the right side, I need to do it on the left side. Okay, so they cancel out, so I end up just getting standard molar enthalpy of this. I end up getting, with my calculator, negative 1,780 kilojoules. per mole. This is the standard mole enthalpy. This is the answer. All right, so these are the 3 green questions of the day. So you got A over here, B over here, and C over here. Try your best. Please pause the video. Try to the best of your ability, and I'll be showing you the answers shortly. This is the answer for A and B. And this is the answer for C.